This video is going to be on topic 2.5. It will deal with multiple choice. So I'm trying to get you exposed to some of the questions that are related to this chapter. So this chapter is about enzymes. So exposing you to different ways in which questions can come to this can help you already tackle the next questions that will come. Okay, so let's start with the first question here. Now remember to always read the question 3 times. The first time is getting acquaintance, getting out of the anxiety. The second time you're starting to understand. By the third time you really understand what the question is. Do not rush on these multiple choice. Also make sure to read the 4 options because sometimes, like for instance the C and D, they both can look right, but one of them is more in detail and that's always the right answer. So reading the first question here, it says, a fever normally in a healthy adult during illness is not usually a problem and can be regarded as a defense mechanism. However, as a fever is higher than 41, it might be dangerous. What is the cause of a possible damage due to the high fever? So basically they're saying, and it's true, usually our body temperature is about 36. So when we're around 39, that means we're actually having a fever, our body is heated up. And sometimes we can handle the 40, right? But once we hit 41, that's we are so dehydrated, and this is most likely that we're going to the hospital. And if we have a temperature of 44, we are practically dead. Now, looking at this, when that means if our temperature is that high, since this is a talk about enzymes, what does that mean? That means one thing for sure, that all of our enzymes in our body, they function around a 36 to 38. That's what they work on. So if you go beyond 38, right? If you go 39, if you go 40, if you go 41, what's happening to the temperature? It's rising. And we know that when there's a very high temperature, the enzymes stop working. So this is the temperature they usually want to work. But if they're hitting here, the enzymes are being what? They're basically being damaged or destroyed. So right here we have options. The first one says the loss of body mass, muscles damage due to shivering, overactive metabolic enzymes, spread of infections. The question again, it says, what is the cause of the possible damage due to high fever? So what happens if you have a high fever? What are the things that can happen to you? Loss of the body mass? No, because body mass has to do with nutrition. So if you're not eating enough, you will lose. Muscle damage due to shivering? No, there are people who have fever where they don't shiver at all. The shiver has to do with your body cooling off and you're trying to warm it up. So it has nothing to do with that. An overactive metabolic enzyme? Yes. Sometimes in the beginning, the temperature might be rising, so the enzyme is working a little bit faster, which is not a good. And that can cause problems later. So C possibly can be, these ones are not. And then the spread of infection, that's not a damage necessarily because you can deal with infection and not damage much things. So the right answer here is the enzymes, because remember, as the temperature rising, the enzymes start working a little bit faster, and sometimes when they're working too fast, they might cause a breaking up of things which can damage. So the answer here is C for sure. Looking for the next question. It is possible to attach a B-galactosidase. Now, here's the most important thing. You already see the word A's here, which that means we're talking about enzymes. So they're talking about this enzyme to alginate beads. Now, alginate beads is these little circle beads, and basically inside these beads, you put in the enzyme. Okay? Now, for the use of production of lactose-free milk. So what it looks like is that you have this test tube right here. And inside you put these beads, and these beads have the enzyme, galactosidase, and they're just putting in here. So it's a bunch of either enzyme. And inside here, you're going to pour milk, right? And the milk is put in here. And in the end, for example, depending what molecules of sugar you have here, the enzymes here will break that, and then here it won't have that sugar anymore. So let's look at the examples. Now, what are the enzymes that have been attached to this way called? Now, the enzymes that we're trying to break these things down here is an enzyme that is breaking the sugar. And the sugar here in this case is lactose, and lactose is broken down here as galactose as well as glucose, right? Now, these enzymes are found in these beads. So basically the bead is right here and the milk is just passing through it, and the enzyme is breaking at this point all the lactose into galactose and glucose. Now, when we say attached, it means how did you attach these enzymes, right, into those beads? The attachment of them in this bead, where it's just the beads holding on to it, this is called immobilized. That means they have been attached to a place and they do not move. That's what immobilized mean. So you put all the enzymes in these beads, and the bead stays in its place. It's the milk that keeps moving in. So in another color, the milk is moving, but the beads don't move. Another milk is coming and the beads don't move. But what do the beads do? The beads keep breaking down all the lactose that crosses that bead, but the bead doesn't move. So the right answer here, it will be the immobilized. It is not inhibited because you're not stopping enzyme, and it has nothing to do with catalyze because every single enzyme is being catalyzed and it's not been activated. What the fact of having a bead and putting the enzyme here, that is known as immobilized. So the answer is B. Now we have another question here, and there's going to be always a lot of graphs when it comes to enzymes. So it's very important for you to understand how enzymes are represented when it comes to graph. So whenever you have a graph, the first thing you have to do is always look at the y-axis. Here it says the rate of reaction, that means how fast the rate of an enzyme is working. And here is how many substrates, that means how many reactants are you putting there. So looking at the graph, it shows an effect of increasing the substrate concentration, which is true. As you can see, look, as you go this way, what's happening? You are increasing the concentration of a substrate. Right? So in this case, it can be any molecules. It can be maltose, sucrose, whatever it is. Okay? And by increasing the concentration, you're increasing the rate, which is true. As you increase, what's happening to the rate is increasing, but it's going to reach a point where it's going to plateau right here. Which means plateau means that it's going to reach to a certain point that no matter how many more substrates you put, the enzymes will not work. Now, what is occurring during the phase dedicated by the Y, which I was just talking about it? So what I'm trying to say is this. Let's just say in your body, there is only 100 enzymes. So if you have one enzyme and one sugar, that's fine. Two enzymes, two sugars, that's fine. And you keep going. But once you reach the 100, right here, it's fine. You have now all the enzymes working. But 101, there is no extra enzymes here anymore. So the extra one here, he cannot do any function. The one will stay waiting. If you put 102, two of them will be waiting. If you put 103, so all the extra substrates above 100 will have to sit there and wait because all the enzymes are already working. So it's not like you can speed the reaction because all the enzymes are occupied. So let's look at which of these four options explains that. The first one says here, the active site of the enzyme is saturated. What does that mean? That means that every enzyme is attached to a substrate. So if there is 100 enzymes and 100 substrates, all of them are already attached. So this one could be, but let's check the other ones. The B says the enzyme becomes denatured. This has nothing to do, if it's denatured, let me just show what the nature would look in a graph. It would mean that instead of going like this in plateau, it would have gone down as in dying, or even more steep like this. That means you're killing the enzyme, so the rate would just completely stop. So it cannot be B at all. C, the substrate concentration has risen too high. Okay, even if it's risen too high, that does not explain what this is stopping. Okay, you can continue increasing as much as substrate as you go in this direction, right? So I'm not erase this. You can continue going. It doesn't matter. You keep going and adding and adding, and you can continue doing this. So it's not necessary about the concentration. So the substrate constraint is not the one in limit. It's not the one that has a maximum amount. So it cannot be this one. The optimal rate is reached. If the optimal rate is reached, it means after it could go down, or it can go up, or it can do whatever. We don't know. So it's not the optimal. It just means that it stops and it continues down here. Because every time it's about optimum, that means it should be going down after the optimum. Let me be more clear again. If any enzyme is reaching its optimum, when it reaches its optimum, if this was the optimum, then the next most common thing to happen to a graph is to go down. So it cannot be saying, oh, it reaches optimum. If it reach then it needs to go down. But now what it did is reach a plateau, which plateau means that you have maximally put all the 100 enzymes into work, so they all are attached. All the enzymes are attaching to a substrate and it's doing its work. So the right answer is here. The one that completely makes sense is A, right? That means all the enzymes have been saturated. Now, what is active site? So just to keep a little bit of refreshing you from the topic for those who still might have a little bit of forgetfulness about this. So the enzyme, so if the enzyme, they will look like this, right? This square right here, this area here is known as the active site. And this is where the substrate, which you can see, the shape has a square shape, and this guy can attach here. This is the substrate, right? So the sub will attach on the active site of the enzyme. So when it comes, it attaches right here on the active site. That's what the active site is, the space inside the enzyme where the substrate will attach. So if all the enzymes are already attached to the substrate on its active site, they all are functioning. So that means they have reached a point where all of them are saturated. And what I mean by saturated, that means all of them are occupied with a substrate. So the right answer here is A. Now if we go for the next question. Here is an experiment. The effect of changing the pH on an enzymatic reaction is tested. So what are we doing? We are checking the pH and how this pH is working in the experiment. Now, which could be the dependent variable in this kind of experiment? See, 2.5 talks about making experiments with enzymes. That's why it's one of those labs that you had to do in class, which you are playing with the enzymes and see how the enzymes are reacting, if they're going faster or slower, depending on the limiting factors. It can be a temperature, it can be a pH, it can be a substrate. So this question usually comes in a multiple choice, trying to test if you know and think about how your labs that you're doing. So once again, what is the question is asking? Which could be a dependent variable in this kind of experiment? So we're saying that we are manipulating the pH. So if the pH is this, that means it's the independent variable. It is the pH. What could be the dependent? Now, if that's pH, that means I might be testing with 3, a pH of a 4, a pH of a 7. Let's put 6 instead of 6, I get 8 and 10. So I'm testing different pHs on the enzyme. What could be the dependent? That means what do I want to see as a result? Like the changes that is happening. So the first one, it says the change of substrate concentration. That's actually what the enzyme is going to be working on, right? So I cannot change the substrate concentration because the only one that can change is the pH, because the pH is the independent variable. Because imagine if I have this 2 with 50 grams of a substrate, and then this I have with 100 grams of a substrate and a pH of 4. I have 150 and a pH of 5. What's wrong with that? Like, not only are you changing the pH, you're also changing the substrate. So now you have 2 independents, so that does not make sense to be A. So A is out of the way. Then B here says the rate of formation of the product. That could be how fast the enzymes are working. Now that makes more logic. Why? Because it's like, imagine you having a test tube at the pH of 2, a test tube in the pH of 4, and a pH of 6, and a test tube with 8, and a 10, right? And what are you putting inside? You're putting the enzyme and the substrate. You're putting the enzyme and the substrate. Remember, they all have to have exactly the same amount of enzyme and the substrate, enzyme and substrate. But you're checking at pH of 2 how the enzyme is working. And then you're checking the pH of 4 how the enzyme is working. And you keep doing this. So you can figure out in which of these pHs is the enzyme working the fast. So B looks more like a promising answer, but let's check the other ones. The one says variation in temperature. Again, it's the same thing about the substrate. If you are changing the pH, the temperature for all of them should stay the same, let's say 30 degrees. Otherwise, you're going to have 2 independents, so it cannot be this. And then change in pH. If the change in pH is already the independent, how can it be dependent also? It makes no sense. So the right answer is B, because we want to see the rate of formation of the product. Now, you're going to be like, what do you mean by the rate of formation of product? Well, think about what is the enzymes actually doing, right? The enzyme, let's say the enzyme is right here, right? And you have the substrate. So when the substrate comes here, now we have the enzyme with the substrate in, right? Oops, this is drawing. And then after this, what does the enzyme do? The enzyme releases the substrate broken down into two pieces. So what is these two? These are actually the formation of the product. So the rate means how fast this enzyme created this product. Now, what if it was a pH of 2? Maybe it goes like it does this in 5 seconds. If it was a pH of 4, it does in 10 seconds to do this process. So that makes more sense. We're checking out to see how fast there is a formation of product, which is the rate of formation of product, which that is answer B. Now, in this question, we have 3 flasks, right? Now, these 3 flasks right here were prepared for analysis of activity of amylase. So the enzymes that we're using here is amylase. So when you start to read that question, already start thinking, what is amylase? Amylase, oh yes, amylase breaks starch into maltose, right? And you can see that ASE here means it's an enzyme. So, okay, you already settled down, you already understood that amylase breaks starch into maltose. And then it says there, in time 0, each of the substrates indicated in the diagram was added. So that means when they started, at time 0, time 0, time 0, how many substrates they had. So all of them had here starting with a starch solution of 4 and a 4% and 4. So that means the amount of sugar on all those flasks were exactly the same. So that's a control. But in here, they were changing the amount of amylase they were putting in there. So right here we had 0.5 of 1% of amylase solution added. Here we had 0.5 distilled water added. And here we had 0.5 of 1% boiled amylase solution added. Now, here we're having different scenarios. What are the scenarios? In the first scenario, we just have a certain amount of what? A certain amount of amylase, right? Just amylase. So that we're just adding an enzyme. That's what we're doing. Here, we're just adding water, no enzyme. Here, we're adding enzyme, but we also are adding enzyme with temperature. So these are 3 different scenarios. All of them are playing on the sugar of starch, but one is just the enzyme, one is just the water, and the other one is an enzyme on a higher temperature because it's boiling. So we kind of already understand what the experiment is. So that's the first thing. Learn the experiments, understand each flask what's going on before you go to the question, because then you already have kind of an idea. The next thing to do is read the question, and as you can see here, which flask could provide support for the hypothesis that heat denatures the enzyme? So when we talk about heat denatures the enzymes, we have to figure out which one of these 3 flasks are stopping the enzyme from working because of the heat. So a lot of students will assume, oh, it's flask 3 because there's a temperature in there. Okay. Now, if you look at the options here, none of them just says 3, except for the D. So this is where students usually will quickly drop, oh, ask 3 at time 0 and again after 15 minutes. They jump to D. And this is where it is so wrong, right? Why is that? Because you have to think of the logic. You have to think here, and they're saying, which flask could provide support for hypothesis that heat denatures enzyme? So, if you follow the trap and say it has to be this, because at time 0, we are putting an enzyme with the boiling, and again, after 15 minutes, we're measuring it. Now, just think for a logic. If you already put the enzyme with temperature in there, and you're waiting for that 15 minutes to see what happens, right? You're just going to do the reaction of the same. Because think about it. If I use that flask, right? If I use that flask, let's look at this. The enzyme is already coming here with already a temperature to do its work. So, and then I place it again. I check it after 15 minutes. Did I really change the temperature here? No, it was kept the same. It literally was kept the same. And if I put again that enzyme with a certain temperature after 30 minutes, what happened to the temperature? It's still the same. Okay? So it will not prove anything. It's just you're putting the same enzyme with the same temperature, you're going to get the same result. Do you agree? Yes, because look again, it's already starting with the same temperature. Okay? Now, I need to put somewhere where I can support that heat will denature the enzyme. But what if I do one without the heat, which is the first one here, and the one with the heat, and look what happens here. Here the temperature would we say that there is no heat, so I would assume that the temperature will be cooler, and this temperature will be a little bit more hot. Now, if I use the flask 1 to compare it to the flask 3, now I can do a hypothesis. Why? Because when I go through repeating this guy here many times after 15 minutes, it will give me a certain result. It will give me result A, agree? But here I have added the temperature a little bit more hot, and I can go through the experiment many times and it will give me another result that will give me result B. So what's the difference between results A and B? It is the temperature. I added the temperature. So now I can compare the temperature to a place that was no temperature rise. And now I can prove that that temperature did kill the enzyme and it was denatured. So the options here, is it 1 and 2 after 15 minutes? No. Let me show you why it would not be 1 and it could not be 1 and 2. Because if I use the flask that has only the enzyme and the other flask has only water, after 15 minutes, he will give me result A, and this one will give me result B, right? But this is without enzyme, so where's the reaction? We can't prove anything. You can't prove that heat kills the enzyme because there's not even an enzyme here. So 2 is out of the question completely. And so is this one because he has flask 2 here, so there's no enzyme in there. So how would you know if you're going to kill the enzyme or not? It just makes no sense. And then, of course, the flask 3, as I told you, it cannot be flask 3 on its own. Why is that? Because if you start with enzyme with a certain temperature already there, it's going to give me result A, agree? And if I'm going to start the enzyme again with the same temperature at the same time, it's going to still give me the same result A. So how am I going to prove, how am I going to compare if it's the same experiment with the same data, with the same movement, with the same temperature? There's no way to prove. So you have to have a comparison to do it. That's why C right here makes more sense. I have a flask with enzyme and I have a flask with the enzyme and the temperature was increased. Now I can see what happens to this as a result and it's compared to the result with the temperature. So now I can compare and see how that temperature actually killed the enzyme. So the rate here might be slow and here the rate might be a little bit faster. So it is comparing flask 1 and 3 after 15 minutes. That's how you can say that the heat denatured the enzymes. So this is a very little bit of tricky and this can fall in easily on the test where they're manipulating with you. So a lot of students don't understand, but whenever you want to play with hypothesis, you have to have something to compare to. So the A and the B, between the A and the B, basically the A has A and the B should be a combination of A plus something else. So for example, A in this case had the enzyme and the other one had the enzyme with the increase of temperature. So what happens, that temperature was able to compare to something that had the temperature not hot. So when you have something to compare, now you can look for the hypothesis and see if it's true or not. Because what I'm doing here is with this one, I'm using this as a control and I'm doing this as an experiment, right? To test the temperature to see if it works. So you're always comparing to a control. So what I did was use flask 1 as the control and flask 3 as one, and then I'm manipulating the temperature. Okay? Now let's go to the next question. Here says, what is the advantage of using lactase, right, which is an enzyme, in an immobilized state in the food of manufacturing industry? So it goes back to that little flask that I told you where you put all those beads and inside those beads they has the enzyme lactase, right? And then the milk is right here going inside. And in the end, what's coming out here? It's coming out lactose-free milk. Why is that? Because the enzymes that was here, which is lactase, what did it do? As the milk was passing through, right, all the lactase that was, all the lactose that was in there was broken down into glucose plus galactose. So right here, you were lactose free. So here is asking, what is the advantage of using this immobilized lactase? Immobilized, again, is these beads here, right, with lactase. So the first one says it functions within cells. It has nothing to do with cells. This is done in a lab. It dissolves multiple solvents. Which multiple solvents are we talking about? We just have one milk here going through this. So it's not dissolving milk. It's breaking something inside of the milk. So it's not that. It converts cellulose to glucose. Lactase is not about cellulose to glucose. Lactase is about, again, it's about lactose broken down to glucose plus galactose. So there's no cellulose in here. So this is definitely also not none of these three. So you can already reject 3, which leaves you with D, which is less likely to become denatured, which is true because what's happening here is they're just mobilized. That means they're just standing still inside these beads, and its job is just to, as the milk passes by, it breaks it down, but there's no chances of destroying it. And the best part is that you keep using again and again and again, and you can make all those milk become lactose free without destroying the enzyme. So the answer is D. And then we have this question here. Again, when it comes to enzymes, they're always going to throw some kind of graph. It's always this, like our presentations of graphs with enzymes. So remember to look at the y and the axis. So here in the y, what we have, the amount of product that is formed, and here how long did it take on the time. And then what do we have here? The amount of products. That means 40% substrates, 20%, 10 substrate, 5 substrate. So these are the reactants. So remember that the substrate, this is the one is going to enter the enzyme, and then the enzyme is going to produce the product, right? So kind of got an idea. Now the graph shows the effect of changing the substrate concentration on an early stage of the enzyme catalyst reaction. So you can see there was a 40%, a 20, 10, 5, 2, or 0% of substrate. And what would that cause when it comes to the product formed? So for example, if you don't put any substrate, obviously no substrate, no product is formed. If you put 2% of substrate, the amount of product will start to rise, but very slowly. If you put 5 substrate, there's going to be a lot more product in the beginning, right? Compared to number 2, agree? So you have a lot more than here. You can compare it this way. If you have 10%, it's going to definitely have a lot more. As you can see, it has a lot more than the 5%. And you can add 20, you can see that it goes a little bit more products in a shorter amount of time. And the 40 is the one that does a lot more products in a way shorter amount of time. So it's easy to look at this graph if you really think like you're putting numbers. So for example, let's say the time is at, let's say here, 10 seconds. Who's producing more product? At 0, there's no product. At 2%, it's right here. So let's say this is 10. And then at 10 seconds, at the 5% of substrate, you probably made 15. At the same 10 seconds, what do you have here for 10 substrate? You probably made 20. In the 10 seconds, you probably made 30. And if you're doing 10 seconds, look at this, you probably made 40. So obviously, more substrate produce more products in the same 10 seconds. So that means, obviously, you're producing a lot more products with more substrates in a shorter time. Now, looking from this, let's look at the options that we have. It says, what can be interpreted about the rate of reaction from the graph? So we have to read very carefully these questions, these options of answers. So the first one we have here is the rate of reaction that increases up to 5 points and then it remains constant. So just looking from that question, we can see here that it's saying rate of reaction increase. That means it's making more product up to a point and then it remains constant. Well, is that true? It's not constant, because if it was constant, what would have happened here is that the lines are not going up. The lines would have gone to start to go straight, and that's not true. As you can see, the lines are keeping going up. Now there's the rate of reaction B, for example, says the rate of reaction increases linearly. When it increases linearly here, what is it trying to say? Is that it's just going straight with increasing substrate concentration. Now, linearly, it would mean that it would just go straight up or completely straight in line, and that's not true. As you can see, the lines are changing. C, it says the rate of reaction increases non-linearly with increasing substrate concentration. Now, that sounds more like it, but let's look at D. Rate of reaction is not affected by any change in substrate. Now, D is obviously, this one is out of complete things. Why am I saying that? Because you do see this, you see effect, right? You see the changes here. There is changes happening. So D is out of the way. And if the rate of reaction was remaining constant, it would basically mean that at a certain point after here, the line would have gone this way. And then the other line would have been gone this way. It wouldn't keep rising. So that would not work too. And then, so if I have to look at this, A is out of this, D is out of this, so I'm stuck between these two. Now, the reaction rate increased linear with increasing substrate. Linearly would have been that the gap between each one of these guys would have been the same if it was linear, but it's not. You can see that here the gap between 40 and 20 is very small compared between 5 and 2. So it's not linear, it's non-linear, because linear means they're in constant pace. And so B is not it, and the right answer is C. C is the right answer because, once again, it is not linear. Linear would be something that is going in the same distance, right? And going nice and smooth. But this is not true. You can see that there is a gap between this compared to this one. So it definitely has to be non-linear. So yes, the rate is increasing as the substrate concentration is increasing, but it's non-linear simply because the differences here between different concentrations are not exactly the same distance, and that means they're non-linear. So these are kind of questions that you want to get exposed. So they're going to talk about the immobilized beads. They're going to give you graphs talking about different enzymes, or they're going to give an experiment done with the enzymes, or remember some of the enzymes. So it's important that you do understand the concept of how enzymes bind with substrates, talk about the different limit reactions such as the temperature, pHs, or substrates. Also talk about the production of milk through the immobilized beads. These are very common questions that comes for 2.5. And that's pretty much it. Thank you.